Alright, in this section we're going to look at trigonometric integrals. In particular, we're going to look at how do we integrate stuff of the form where we're multiplying powers of sines and cosines and powers of secants and tangents together. And I should just mention the techniques for secants and tangents would also work for powers of cosecants and cotangents. Now, we already know how to do some of these, right? Some of these we can do with a simple u substitution. If you look at, in part A, we've got sine to the fifth x times cosine x dx. Well, here you can let u equal sine x, and then du is cosine x dx. And when we rewrite this with u's, it looks like the integral of u to the fifth du. And that's a power rule integral, so we get 1/6 u to the 6 plus a constant, or 1/6 sine to the 6th of x plus a constant. In this next one, there's a couple ways we could do it, but the simplest really is let's rewrite it by peeling off a factor of sine and writing it toward the end. So I'm going to write the secant to the fourth as secant cubed times secant. And then we have times tan x dx. And in this integral, if we let u equal secant x, then its derivative, du, is secant x tan x dx. So here's our du at the end, right? Here's our u to the third power. Writing it with u's, integral u cubed du, that's a power rule integral, so we get 1/4 u to the fourth, or 1/4 secant to the fourth x plus a constant. So we were able to make a substitution and turn the trig integrals into this power rule integral. And by and large, like a lot of these problems, that's what is going to happen. Only it'll be kind of an extended version. Like maybe it won't just be turned into u to the fifth, but maybe some polynomial with u, so like several terms. To help us with this process, in this section, working with the integrals that we'll have, we're going to want these identities handy. So the Pythagorean identity, there it is with sines and cosines. We've seen how we can find the two other versions, the one that deals with secants and tangents, and the one that deals with cosecants and cotangents. And then depending on what the powers are, we may find it helpful to use one of these half-angle identities. So in this section, we've kind of broken it up into different cases. We're going to start with the integrals involving powers of sines and cosines. And there are three cases here, which we can, I guess, really think of in terms of two cases. The first two cases talk about what if the power on sine is odd and positive. The second case says, what if the power on cosine is odd and positive? Basically, the techniques we use in these two cases are the same. We want one of those powers to be odd and positive. And when that's the case, whichever one it is that's odd and positive, you're going to use Pythagoras to kind of help you. You're going to peel off a factor and use Pythagoras to deal with the remaining factors. So I'm going to show you how it works in this first one. Notice here, the power on sine is odd and positive. So I'm going to peel off a factor of sine x and throw it at the end. The whole idea behind doing that is that that sine x dx at the end is going to be our du. And it seems odd that we're kind of thinking about du before we've chosen u. But if we're saving a factor of sine x at the end to be our du, then must be we're thinking our u will be cosine x. So I'm going to write this as sine squared x times cosine to the fourth x times sine x dx. We are thinking here that u is going to be equal to cosine x, so that du is minus sine x dx. I'm going to deal with making the substitution later, but I'm just sort of putting that in my mind. Now, if u is cosine x, I want the rest of this integral to be able to be written with u's, which means we're pretty pleased at this cosine to the fourth there, but we need to do something about this sine squared. And that's where this Pythagorean identity is going to be useful. We know that sine squared x plus cosine squared x is equal to 1, so sine squared x is 1 minus cosine squared x. And we are going to make that substitution. So we have 1 minus cosine squared x times cosine to the fourth x times sine x dx. Now we have this sine x dx at the end. I can tell, I mean, we're just about ready to make our substitution. We need this negative there, so I'm going to throw in a factor of -1, compensate out there, outside. Now let's put in our u's. If u is cosine x, then cosine squared is u squared. So this is 1 minus u squared. Cosine to the fourth is u to the fourth. When we write this in terms of u's, here's what it looks like. Negative integral 1 minus u squared, in parentheses, times u to the fourth du. Now, it isn't something that we're ready to just jump in and integrate, but we're very close. At this point, we're going to do some algebra. Let's distribute that u to the fourth. So we get negative integral of u to the fourth minus u to the sixth du. And this is a polynomial, so still a power rule integral, right? This is very similar, you know, like in essence to what we were doing here in example A, in part A of example 413. We just had to extend it. We had to do a little bit more work to set us up. We had to be really intentional about kind of peeling off that factor of sine and then using Pythagoras. But the result is essentially the same, an integral for which we can just use the power rule on. So this is negative, parentheses, if we use the power rule, 1/5 u to the fifth minus 1/7 u to the seventh plus a constant. Now I'm going to do two things. I'm going to put the x's back in. I'm going to put cosine x back in for u, and I'm going to distribute this negative. So we got negative 1/5 cosine to the fifth of x plus 1/7 cosine to the seventh of x plus a constant. All right. So that finishes up that one. In the next example, you know, I mentioned before, these first two examples are kind of the same type of situation. We're looking to make sure that we have an odd positive power on either sine or cosine. So in the last one, that odd positive power was on sine, and this time our odd positive power is on cosine. So I'm going to do the same thing. I'm going to peel off a factor of that function, in this case cosine, throw it at the end. Right away, we are thinking ahead of time. Look, if cosine is, if I'm throwing that at the end, I'm thinking that's going to be my du, and so u is going to end up being sine x. Let's see how this looks once we throw that factor at the end. You get cosine to the fourth x times cosine x dx. Alright, so I'm just going to kind of write this out. We are thinking u is going to be equal to sine x, so that du is cosine x dx. The reason that we're picking the odd power, right, to choose which function we're going to peel off a factor of to throw at the end, is that when I peel off that one factor, I'm left with an even power of that remaining, of that function, right? So I peel off a factor of cosine, I'm left with cosine to the fourth, an even power. And an even positive power on sine or cosine, I can rewrite using the Pythagorean identity. So if I'm thinking that my u is equal to sine x, I want to write the rest of this function, or the rest of this integral, in terms of sines. So I'm pretty pleased about that sine squared right there, but we got to do something about this cosine to the fourth, and that's where Pythagoras is going to help us out. We know that sine squared x plus cosine squared x is equal to 1. So cosine squared x is 1 minus sine squared x. Now what we have is cosine to the fourth. And I mentioned that we can use Pythagoras for any even positive power. So cosine to the fourth is just the square of 1 minus sine squared. So let's make that substitution here. Cosine to the fourth is 1 minus sine squared x squared times cosine x dx. So now I've got my cosine x dx at the end. There's my du. Everything else is written in terms of sines. So let's make our substitution. Sine squared is going to be u squared. So this looks like integral u squared parentheses 1 minus u squared squared, so we're squaring those parentheses, times du. Everything is accounted for, right? Everything comes directly from the integral above. And this integral that we have written with u's really is a polynomial. It isn't multiplied out, but it's a polynomial. I got positive integer powers on u. Let's do some algebra and expand this. If we FOIL out the 1 minus u squared, we get 1 minus 2u squared plus u to the fourth. And then we'll distribute that u squared. So we've got u squared minus 2u to the fourth plus u to the sixth. du. And it's a power rule integral, just like the one before it, just like that simpler one in the beginning, right? This took more work to get there, but we're using algebra, we're using Pythagoras to help us turn this trig integral really into a polynomial. All right, let's integrate. We get 1/3 u cubed minus 2/5 u to the fifth plus 1/7 u to the seventh plus a constant. And now it's all over but the shouting. We're just going to throw our sine x back in for u. So we get 1/3 sine cubed x minus 2/5 sine to the fifth x plus 1/7 sine to the seventh of x plus a constant. If your power, if the power on sine or the power on cosine is odd and positive, we have a path forward. If they're both odd and positive, take your pick. It'll work either way, all right? Now, what we don't know yet is, what if we don't have that odd positive power? What if we just have even powers on sines and cosines? So if the powers of both sine and cosine are even and non-negative, so we don't have powers of sines and cosines in the denominator, but if we have even non-negative powers on sines and cosines, this is where the half-angle identities will be useful. So we're going to use the half-angle identity to rewrite this cosine to the fourth x. So let's do some of this work. So the half-angle identity looks like this. Cosine squared x is equal to 1 plus cosine of 2x. Notice that the argument inside the function changes all over 2. And we have cosine to the fourth x, so we're going to square both sides. So I'm going to square the top and square the bottom. So we've got a factor of 1/4. And I'm going to FOIL out the top. So we get 1 plus 2 cosine of 2x plus cosine squared 2x. Now, we can rewrite, using this half-angle identity, we've rewritten cosine to the fourth of x in terms of we have a constant, we have a cosine, but then we still have this even power, right, on cosine there. I'm going to use half-angle again just on that part. So inside the parentheses now, 1 plus 2 cosine 2x plus, and let's see, this is a fraction, all over 2. It's 1 plus cosine of double that angle, so cosine of 4x. It looks a bit like a mess right now, but I'm going to distribute this factor of a quarter. One-fourth plus, let's see, a quarter times 2 is a half, cosine 2x plus, let's see, this is 1 plus cosine 4x all over 8, right, 4 times 2. So I've got a 1/8 plus a 1/4 term. I'm going to do one last thing to rewrite this. So we get 3/8 plus 1/2 cosine 2x plus 1/8 cosine 4x. Alright, so here's all the work leading up to this. Now we're going to be able to rewrite this integral. And I think I got plenty of room. Yeah. So I'm going to call this down here. Integral of cosine to the fourth is the integral of this whole thing we just found. Now we've got all these different terms, so I'm going to split it up over addition. I'm going to split up the integral, and while I'm at it, I'm going to kind of pull out these constant factors outside of their own integrals. So we've got the integral of 3/8 dx plus 1/2 integral cosine 2x dx plus 1/8 integral cosine 4x dx. So notice that we're not going to need to use Pythagoras or anything. We have the integrals we have are the integral of a constant, we know how to do. And the other two are just integrals of the cosine function. Cosine of a linear, right? Like just a constant times x. We know that because we know the integral of cosine. The integral of cosine is sine. These just require simple u substitutions. I'm not actually even going to write them out explicitly. I just know that in the middle one here, if u is 2x, in order to have du, I need a factor of 2 here. And I'll compensate with a factor of a half. I need a factor of 4 in this one, and the last one, compensate with a factor of 1/4 out here. So now these are both of the form integral cosine u du. And we know the integral of cosine u is sine u. So let's integrate all of them now. The integral of 3/8 dx is 3/8 x plus 1/4. The integral of cosine u is sine u, so that's sine of 2x plus the last one we have 1/32. The integral of cosine u is sine u, so that's sine of 4x plus a constant. All right, now we're going to look at integrals that involve factors of secants and tangents. When we were doing the sines and cosines, our guiding facts that we use were that the derivative of sine is cosine and the derivative of cosine is negative sine. That's why we always just peeled off a single factor of one of those functions to be our du, and then focused on maybe turning the remaining factors into what we needed using Pythagoras. With secants and tangents, of course, we're going to remember that the derivatives are different, right? The derivative of secant is secant times tangent, so we need a factor of each. The derivative of tangent is secant squared. In this case, our first case of secants and tangents, we're dealing with if we have a power on secant is even and positive, then we'll save a secant squared. If you're starting with an even positive power on secant and you save a secant squared, you're still going to be left with an even positive power on secant. So, and that means that we can use Pythagoras to help us convert the remaining factors. So here's our even positive power on secant, secant to the fourth. And so we're going to peel off a secant squared factor, throw it at the end. When we do that, it looks like integral secant squared 3x tan 3x times secant squared 3x dx. And if I'm saving secant squared at the end, the idea is that that'll be my du, so I want my u to be equal to tangent. I'm just going to write that out up here. U is equal to tan of 3x, so du is 3 times secant squared 3x dx. So I want the rest of this function just written in terms of tangent. So the power, or that factor of tangent in the middle, I'm pretty pleased with. We got to do something, though, about this secant squared. So that's what we're going to use Pythagoras for. So remember that sine squared of theta plus cosine squared theta is equal to 1. That's true regardless of what our theta is, even if our theta is 3x. If we divide through by cosine squared, we get tan squared theta plus 1 equals secant squared theta. So I'm going to use that to rewrite that secant squared. Secant squared turns into tan squared plus 1. Now, if we're getting ready to make our u substitution, we've got the rest of this function written in terms of tangents, which is great. We just need this factor of 3 here, so I'm going to throw that in, compensate with the 1/3 outside. And now, rewriting this with u's, we have 1/3 integral parentheses u squared plus 1 times u du. Now we can kind of have an algebraic path forward, right? We're going to distribute that factor of u. We got u cubed plus u. And now we can integrate using the power rule. So we have 1/3 times 1/4 u to the 4th plus 1/2 u squared plus a constant. And now it's all over but the shading. We're just going to put our tan 3x back in for u, and at the same time I'm going to distribute this factor of 1/3. So we get 1/12 tan to the 4th of 3x plus 1/6 tan squared of 3x plus a constant. So if the power on secant is if the power on secant is even and positive, we have this technique available to us. Another technique, depending on the powers and how they look, is that if the power on tangent is odd and positive, then we can save a secant tangent factor. And if you're saving secant tan at the end, the whole idea is that we're thinking that our u is going to be equal to secant, because the derivative of secant is secant tangent. I'm going to go back up here and just note that The power on tangent in this problem is odd and positive. So we did this problem using the technique listed here in item 1, but the one we're about to see would also work for that problem. So we've got a secant tangent factor that we're going to peel off. The first thing I'm going to do, I guess, is just rewrite this integral. I've got a square root of secant in the bottom, so I know that's a negative 1/2 power. So we have tan cubed x times secant x to the negative 1/2 power dx. And we're going to save a secant tangent factor. Maybe you're scratching your head at this and thinking, I don't have a really, I mean, we have negative power tangent, but that's fine. You know, we're just going to use the rules of exponents. Secant to the negative 1/2 is equal to secant to the first, positive 1, times secant to the negative 3/2. That's how we're going to make this work. So let's rewrite this. If I'm saving a secant tan, if I'm kind of peeling off those factors for the end, that means that what we're left with here is tan squared x times secant x to the negative 3/2, and then times secant x tan x. You can check with the rules of exponents, convince yourself that this integral, the function we've written in this integral here, is equal to the one directly above. So we're saving secant tan for the end, and as I mentioned before, that means we're thinking that our u is going to be secant x. So I'm just going to write that out. Now that means I want everything else written in terms of powers of secant. I'm pretty pleased with that secant to the minus 3/2, but we have got to do something about this tan squared. Again, I'm going to scroll back up to the previous problem because we know what that is. Tan squared plus 1 is secant squared, and that means that tan squared is secant squared minus 1. So I'm going to make that substitution here. So we got secant squared x minus 1 times secant x to the negative 3/2 times secant x tan x. Now, there's no factors that we need to throw in to make our du work, right? We have it perfectly. So we're ready to make our u substitution. Let's write this integral with u's. We have the integral of u squared minus 1 times u to the negative 3/2 du. And we know how to proceed with this. Let's distribute that factor of u to the minus 3/2, and then we'll have an integral that we can use the power rule on. So let's see, u squared times u to the minus 3/2. I'm going to add the exponents. 2 plus a negative 3/2 is 1/2. Minus u to the negative 3/2. So now we can use our power rule. I'm running out of space here, so I'm going to move over to the right. Using the power rule, we get 2/3 u to the 3/2 minus, using the power rule there, I'll have u to the minus 1/2 times a negative 2 plus a constant. Now I'm just going to clean this up, put the u back in, or the secant x back in for u, rather, and this will be 2/3 times secant x to the 3/2 plus 2 times secant x to the negative 1/2 plus a constant. And there is our integral. Alright, so in the next section here, suppose we have no secant factors at all. The power and tangent is even and positive. Then we can convert a tan squared factor to secant squared. And then we just reevaluate and see if we're ready to integrate, or maybe we might need to repeat the process. So I'll note first, this is a definite integral. I'm going to just use this technique to find the indefinite integral first, and then we'll know what function to put our limits on. So the integral of tan to the fourth x dx. They say convert a tan squared factor to secant squared. Okay, so the way you convert tan squared to secant squared is by using Pythagoras, right? Pythagoras says sine squared x plus cosine squared x equals 1. I always have to start out Pythagoras by writing out the sines and cosines 1. And we divide through by cosine squared, we get tan squared x plus 1 equals secant squared x. And so that means tan squared x is secant squared x minus 1. Okay, so this is tan squared times tan squared. I'm going to just convert one of these to the secant squared using Pythagoras, so I'll say that second one. Doesn't really matter which one. Okay, so we did that. Convert a tan squared to secant squared, then expand. So what that means is multiply it out. I'm going to distribute that tan squared factor. So we got tan squared x secant squared x dx minus, I'm expanding it and splitting up the integral at the same time, minus the integral of tan squared x. And now we just want to kind of reevaluate where we are, see if we know how to do these integrals. The first one, tan squared secant squared, that's one that we do know how to do. A simple u substitution will work on that because the derivative of tangent is secant squared. So this one we can do by letting u equal tan x, and then du is secant squared x dx. The next one, though, the integral of tan squared, we're kind of back where we started. Not exactly where we started because it's not the fourth power, but it's an even power, positive power, and we have no secants. So this is where we're going to do the repeat if necessary. So I'm going to rewrite that tan squared as secant squared minus 1. So let's see, I'm going to just rewrite this all exactly as is. I guess, except I'm going to go ahead and make the u substitution, I guess, in the first one might as well. That's the integral of u squared du minus integral. This is secant squared x minus 1. And now I'm going to split up this integral. So I got the integral of u squared du minus the integral of secant squared x dx, and then plus the integral of 1 dx. It's a plus because we're distributing, right, this minus when we split it up, and so that ends up being a plus 1 there. Now, all of these are ones we know how to do. Obviously, the first one's a power rule. We know the integral of 1 at the end, right? We know how to integrate a constant. And the second is an integral we know. The integral of secant squared is tangent. So now let's just integrate the whole thing. You get 1/3 u cubed minus tan x plus a constant. I'm going to now put the tan x back in for u here, so you get 1/3 tan cubed x minus tan x plus a constant. This is the indefinite integral of tan to the fourth x dx. That's what we have here. Now we're not stopping at this point because we need to evaluate the definite integral, but we've done the hardest part, right? We've integrated it as a function. Now we know what we're going to put our limits on. So they wanted us to integrate tan to the fourth x dx from 0 to pi over 4. So that's going to be this function here. That's what we're going to throw our limits on. We don't need a plus c in a definite integral. So now we're going to plug in the upper limit. And now for the lower limit. So tangent of pi over 4 is 1, and tan cubed is of pi over 4 is 1 cubed. So this here is 1. This is 1. For the other stuff, tangent of 0 is 0. So of course tan cubed is 0, is 0 cubed, still 0. So this, actually, when you plug in the lower limit of 0, the whole thing just zeroes out. And what we end up with is 1/3 minus 1 plus pi over 4. And we could simplify that. 1/3 minus 1 is a negative 2/3. So we'd call this pi over 4 minus 2/3. And there it is. You can approximate it if you like, but, you know, we have a nice exact solution here. All right, so we've covered a couple of bases here. One of the scenarios we might encounter is if our integral is just an odd positive power of secant and no tangents. If that's the case, we already know how to do that. You're going to use integration by parts. It could require a repeated use, but see example 4.11 that we did in the last section. And then if none of these guidelines applies, you can always try converting your integral to sines and cosines and see what it looks like. So in example 420, we've got the integral of secant over tan squared. Now, secant is 1 over cosine, is the reciprocal of cosine, so that's like a factor of 1 over cosine x. And then dividing by tan squared is like multiplying by cotan squared. And cotan is cosine over sine. So that tan squared in the bottom becomes this fraction cosine squared x over sine squared x. We can do some simplifying here. We can cancel a factor of cosine. So now we have cosine x over sine squared x. There's more than one way you could proceed, but I'm going to suggest, let's write this as cosine x over sine x, sine to the first x, times 1 over sine x. And I think this is maybe the fastest way to do this integral, because cosine over sine is cotan x, 1 over sine is cosecant x. Usually we write that product, or we're used to seeing or writing that product in the other direction, cosecant cotan. The integral of cosecant cotan is minus cosecant plus a constant. You could also have written this as sine x to the minus 2 times cosine x dx, and use u equal sine x and power rule. It's a power rule integral. So you can have a go at that. You'll see that you get the same thing. It won't come out to negative cosecant initially, but it will come out to negative 1 over sine, which of course is equal to negative cosecant. And again, like I said in the very beginning, the techniques we have for secants and tangents, they'll work for cosecants and cotangents too. Here we have cosecant to the fourth, cotan to the fourth. And when you have an even positive power on cosecant, you can save a cosecant squared for the end. So let's peel off that factor and see what it looks like. And if we peel off a cosecant squared, we're left with a cosecant squared x in the beginning, cotan to the fourth x, and then cosecant squared x at the end. The whole idea behind doing that is that cosecant squared, or negative cosecant squared, is the derivative of cotan. So the idea behind saving that at the end is that we let u equal cotangent, cotan x, so that du is minus cosecant squared x. That means that we want the rest of this integral written in terms of cotangents, and we can do that with the help of Pythagoras. So we're pretty psyched about that cotan to the fourth right there, but we need to do something with the cosecant squared. So Pythagoras says sine squared x plus cosine squared x is equal to 1. To get the version that deals with cotans and cosecants, we're going to divide through by sine squared. And if you divide through by sine squared, you get 1 plus cotan squared x equals cosecant squared x. So that's what I'm going to use to make a substitution here for cosecant squared. That's 1 plus cotan squared now. We're almost ready to make our substitution, but we need this negative. You know, du is a negative cosecant squared. We need to throw in a factor of -1 and compensate outside with a negative. And now we can make our substitution. So 1 plus cotan squared is 1 plus u squared, in parentheses, times u to the fourth du. Everything is accounted for, and we have a path forward. Let's distribute that factor of u to the fourth. U to the fourth plus u to the sixth du. And now it's a polynomial. Let's integrate. 1/5 u to the fifth plus 1/7 u to the seventh, and then plus a constant. Now all that's left to do is to put cotan x back in for u, and I'm also going to distribute that negative. So we get a minus 1/5 cotan to the fifth of x minus 1/7 cotan to the seventh of x plus a constant. And there's our integral. Right, the last thing that we're going to look at today is what if we have some products that involve different arguments or different angles. And in particular, we're going to look at sine-cosine products. So we have a sine times cosine, but the arguments are different, right? All the ones that we've been dealing with, our arguments have been the same, right? And that's what makes the whole, u substitution work, right? If the derivative of sine 2x is cosine 2x times 2. It's not cosine x or cosine 3x. You can't just change up the argument like that. So if we see a product of sine and cosine and the arguments are different, we got to throw away like the other techniques that we were looking at. Those aren't really going to work. But what can work are some of these product to sum formulas. None of these are anything that you're expected to memorize. They're on a sheet of trig identities that were found, I think, in the beginning of chapter 2. They're also found in the book. They're also found, obviously, here in our notes, and about 1 million places online. But what you do want to do is just remember, oh, there are these identities that exist. Let me go find it and use it and see if it makes it better. So here we have these 3 identities. One if you have sine times sine, one if you have sine times cosine, and one if you have cosine times cosine, right? And again, the arguments are different, right? We have different coefficients on x in here. So this example, we have a sine times cosine with different arguments. So that'll be this middle formula, where m is equal to 5, and n is equal to 4. And so I'm going to start out just by rewriting the sine 5x cosine 4x using this formula here. So I got 1/2 times sine of m minus n, so 5 minus 4x, plus sine of m plus n, so that's 5 plus 4x, dx. Oh, and I guess, right, that It's all inside the sine function. So we have 1/2 sine of x. Whoops. Let me start again. Let me yank that factor of a half outside. That'll be better. 1/2 integral sine of x plus sine of 9x dx. Now I have a sum of two different functions, but they're both just sine of a constant times x. I think we know how to integrate both of those. I'm going to split up this integral. When you split up the integral, both of those integrals need this factor of a half. So we get 1/2 integral sine x dx plus 1/2 integral sine of 9x dx. The first one we could just integrate, but the second one we'll need to throw in a factor of 9, right? We'd be integrating sine of 9x, thinking u is equal to 9x, right? We need a factor of 9 to make sure we have our du here, and then we put in a factor of 1/9 outside to compensate. Right, now these are both of the form integral sine u du. The integral of sine is a minus cosine. So this is minus 1/2 cosine x minus 1/18 cosine of 9x plus a constant.